Good evening and welcome to this lecture. So last time we left at the point where we had got this part, that is the Laplace transform. So we had seen how to transform functions using the Laplace transform. So we went ahead and looked at the inverses. So we also looked at the inverse, the Laplace inverse of these functions. We were able to look at the Laplace inverse. So I told you to go through that. So that now, today, we'll focus now on the applications of these Laplace transforms to derivatives. But today, basically, we'll measure on the Laplace transform of derivatives. So basically, when you say Laplace transform of derivatives, you can be having equation like f prime of t. So we want to know that in terms of the Laplace transform. So for instance, the Laplace transform of the first derivative. So this L simply means the Laplace transform, and this f prime of t, it means the derivative of the function f of t. So it will be expressed in this form. So it will be S Laplace transform of f of t minus f of 0. So this is standard form of the Laplace transform of f prime of t. For the second derivative, the Laplace transform of the second derivative of t will be given in this form. It will be given in this form. And then in general, for a general case, if you're asked for any derivative, be it fifth derivative, 10th derivative, so you will always be using this formula. This is the generalization. For instance, when n is 1, assuming that n is 1 here, meaning that if you replace n with 1, then this term will have s times this, and then minus, so 1 minus 1 will be 0. So this term will be 0. And then, of course, there will be no these other terms. So you'll only be having s Laplace transform of f of t minus f of 0, and so on. So basically, how they arrived at this, we can be able now to follow. Let us see how they were able to arrive at maybe this point. How did they arrive at that point? So from the definition of Laplace transform, in our previous lecture, we were able to define the Laplace transform, and we said that the Laplace transform of the function f of t is equal to the integral from 0 to infinity, exponential minus st times f of t dt. So this is what we usually, your function that you're transforming is here. You are transforming f of t. So as you can see, you have to introduce the integral sign, and then from 0 up to infinity, and then the exponential minus st dt. Then it follows that now you have to integrate this using the knowledge of integration that you learned in that is second year, or basically in calculus 2. From your knowledge in calculus 2, you are taught how to integrate, to integrate such functions. And basically, you will apply the concept of Laplace. Most of you are aware of it.
Most of us, can I be on that? I said most of us we are.
So you will apply Laplace when choosing, that is your u, and so on, and so on. So using integration by parts, This method is normally known as the integration by parts. So we need to see which value are we going to choose to stand for, that is the first one here. So which one do we choose to stand for u? Following this LaTeX rule. So as you can see, we have chosen the exponential. We have chosen the exponential because it is the one. It is the one which is appearing first. It is the one which is appearing first. That's why we are saying that u, we let u to be exponential minus st. Exponential minus st. Meaning the one that is remaining. The other values that are remaining, that is exponential, we have taken exponential st to be u. So we are remaining with f prime of t dt. So this will be our dv. That will be our dv. So now you require to obtain du and v. So du is basically obtained from u by differentiating u. So if you differentiate u with respect to dt, then it is clear that you are going to get du being negative s exponential minus st dt. If you integrate dv with respect to dt, then the integral and d normally cancels out. And then if you integrate f prime of t, then it will become f of t. That's why we're saying that our v is f of t. So going ahead, now you need to replace it in the formula for integration by parts. If you can recall the formula for integration by parts, then we normally have uv minus of v du. So that is normally the order when it comes to integration by parts. When it comes to integration by parts, that is normally the order. So basically, Laplace transform of f prime of t will be equal to, so you need to identify your u. So our u was exponential minus st, and then v was f of t, and then the limits are from 0 to infinity. So minus the integral from 0 up to infinity. So here we have v, and v is f of t, and then we have dt, which is, in this case, it is du. In this case, we have du, and the du is whatever you have here. So this is our du. And then if you apply the limits, if you apply these limits, we know that exponential of negative infinity. So this is a fact. So exponential negative infinity is 0. So exponential of negative infinity will be 0. So for the first part, we'll have 0 minus. For the second part, you are now inputting, so it is now minus, minus. You are putting the lower limit, which is 0. Exponential 0 is 1, so we'll have f of 0. So it is minus f of 0. So plus, we know that this minus and minus will make us to obtain the plus here. And then this s is a constant, so it can come outside as s. So we have the integral from 0 up to infinity, exponential minus st f of t dt. And if you remember from the definition of Laplace transform, from the definition of Laplace transform, the Laplace transform of f of t, we have seen that in our previous lecture. So we had said that this is the Laplace transform of f of t. So the integral from 0 up to infinity exponential minus st f of t dt is basically like saying the Laplace transform of f of t. That is basically the Laplace transform of f of t. So meaning now whatever we have here, this one will become this. And then because of the minus now, we rearrange, we'll have minus f of 0. So this is the first derivative here, whatever we have here. You have seen how basically they were able to manipulate this integration to get this, the first derivative, to get the Laplace transform of the first derivative. So moving ahead, we know that the Laplace transform of the second derivative is given by the integral from 0 up to infinity exponential minus st f of f double prime of t dt. So basically we are applying also integration by parts, and basically we know that we have to choose u to be exponential minus st, and then dv will be the remaining part, that is f double prime of t dt. So also you need to obtain du, that is by differentiating u, and you obtain v, that is by integrating dv, by integrating dv. Then we know that after doing that, after obtaining the u, v, dv, and du, then you apply this formula. You apply this formula, then meaning that we'll have into bracket exponential minus st f prime of t from 0 up to infinity minus the integral from 0 up to infinity. We have v, this is our v, and then this is our du. And as we said, exponential of negative infinity is always 0. So we remain only with minus f prime of 0 plus s is a constant, and then this minus and minus, we have a plus here. So the integral from 0 to infinity exponential minus st f prime of t dt. So, and if you can look keenly, this part, if you look at it very keenly, this part simply represents the Laplace transform of f of t. So it is basically the Laplace transform of f of t, which is shown here. So basically, we are supposed to replace this. We replace her in the place of that is this one, because it is the Laplace transform of f prime of t. Or basically, you can write in this form. So you have s Laplace transform of f prime of t, and then minus f of prime of 0. So which will be equal to, we know that Laplace transform of f prime of t is the one that is given here. The one that is given here. So we are multiplying it by s. We are multiplying it by s, and then minus f prime of 0. So if you open this bracket by multiplying all through by s, then you'll have s squared Laplace transform of f of t minus f of s type of 0 minus f prime of 0 minus f prime of 0. So by induction, now having done the two, having done the first derivative, that is f prime and f double prime, then you can easily be able to deduce and come up with an induction for depending any kind of a derivative that you can be given. It becomes very easy for you to transform that derivative to Laplace transform. That is by using this induction. By using this induction, for instance, if n is equals to 2, If n is equals to 2, then we know that we are referring to f double prime. We know that we are referring to Laplace transform of f double prime, which will be equal to, so we have s, so n is 2, and then we have Laplace transform of f of t. Transform of f of t, and then you have said that n is 2, so we have 2 minus 1, we have 1, so it is minus s f of 0 so 2 minus 2 is 0, so s to power 0 so we have 2 minus 2 is 0, meaning that now s to power 0 is 1, so we have minus f prime of 0. So we have that. So if you look at whatever you have here, then it's the same thing. It is the same thing that we obtained previously. So as you can see now, this general case will be very important for you to understand if you don't want to go through the long process of integration. Then you need to have this in mind. But sometimes you can be provided with SMP tables. They normally have these transforms, which will always help you. So let us look at the application of Laplace transform in solving differential equations. So now these Laplace transforms, they can be applied in solving the differential equations that we normally know. So other than the other methods of solving these differential equations, this Laplace transform just work the same as the other methods. It works the same as the other methods. So let us consider a second order differential equation. So as you can see, this is a second order differential equation, the one given here, which can also be written in this form. It can also be written in this form, that is a double prime plus b y prime plus cy is equal to f of t. So a, b, and c are constants here. So taking the Laplace transform on both sides. So usually the first step to do here, if you are given your differential equation in this form, so it is better first of all to write your differential equation to take this form. It is better to write your differential equation in this form. Then after doing that, you have to take the Laplace transform on both sides. So it is a must you take the Laplace transform on both sides, because if you take the Laplace transform on one side and then you leave the other one, meaning that whatever you are doing will not be mathematically correct. Whatever you do on one side should also apply to the other side. So now this is simply telling us that we are applying the Laplace transform on both sides, and we said that a, b, and c are constants. So a can come out, so we have Laplace transform of y double prime plus b Laplace transform of that is y prime plus c Laplace transform of y is equals to Laplace transform of f of t is equal to Laplace transform of f of t. So f of t can be any kind of a function. So in this case, we don't know the nature of f of t. So f of t is basically an arbitrary function. But later on, when we'll be handling some examples, we will see that f of t is taking different kind of functions. So basically, what we'll have here, from whatever we have seen on top here, then the Laplace transform of y double prime. So a is a constant. We have into bracket, the Laplace transform of the second derivative is whatever we are having here. So which will be s squared Laplace transform of y minus s y prime y of 0 minus y prime of 0. And then plus, for this one, b Laplace transform of y prime is basically like the same as the Laplace transform of f prime. It is the same as the Laplace transform of f prime. And we saw that the Laplace transform of f prime is whatever you have here. Whatever you have here. So we have s Laplace transform of y minus y of 0. And then obviously this one will remain the way it is as c times Laplace transform of y. Because this is our reference point. We are changing only the primes. We are changing the primes to be just the y plane. As you can see, the reference point is the y plane. So this y plane will just remain the way it is. You just need to maintain the term, the Laplace transform, and then is equal to Laplace transform of the right side. So if you are given the initial conditions, so the initial conditions are the one that helps you to identify these arbitrary constant, the A, B, and C. So the initial conditions normally assist you in solving them to get the value of the ys. So, and how do you get the ys? That is by getting the inverse. You need to get the inverse so that you can get your solution. So let us look at an example so that we can understand better what we mean. An example will help us in getting a better understanding. So we have been told to solve the following differential equations using the Laplace transform method. So the equation is, we have y double prime minus 6y prime plus 9y is equal to t squared exponential 3t subject to the initial conditions. So we have been given the initial conditions as y of 0 is equal to 2 and y prime of 0 is equal to 6. So what do we need to do? So what we need to do is, first of all, we need to take the Laplace transform on both sides. First of all, we need to take the Laplace transform on both sides. So meaning, what we'll have will be what? So we'll have the Laplace transform of y double prime minus the Laplace transform of y prime plus 9 Laplace transform of y, and then plus the Laplace transform of this function. That is exponential 3t, and then times t squared. So the Laplace transform of y double prime, the Laplace transform for the second derivative is what we know already. Already we know this from up here. We know where it is coming from. So if you are given to obtain the Laplace transform of the second derivative, of course you get your answer being this, and then the Laplace transform of the first derivative is whatever you're having here. So these are the things that we know already. And then this part will remain the way it is, and then is equal to 2 over. So the Laplace transform of exponential 3t times t squared. So this one we saw in our previous lecture. That is the Laplace transform of exponential 3t times t squared. So if you can just go back there, let's go back there and see what was happening. So this is where we were.
Unatumia light saizi.
So from this general case, and in our case, we have exponential minus st, and then you have t squared. You have t squared. So meaning, if we have t squared, then our n is 2. We know that our n is 2. So we have 2 factorial over s minus a. And our s there, what is our s from there? So we need to know the s for our given equation. So we need to know the s. So from the given equation there, as you can see, our s is basically 3, or our a. Our a is 3. So we have said that our a is 3. So coming back here, then our a is 3. So we have s minus 3 into bracket. So n plus 1. So and our n is 2. So 2 plus 1 is 3. I know that 2 factorials are simply 2. So our answer will be what we are seeing here. The answer will be what you are seeing here, 2 over s minus 3 to power 3. So now it is clear to you where you are obtaining the Laplace transform of is another part. But it is from the previous part. So now, having applied the Laplace transform on both sides, the next thing that you do is you apply the initial conditions. You need to apply the initial conditions, whereby we had said that y prime of 0 is equal to 2, and y prime of 0 is equal to 6. So you need now to come here. You need to come here and look at whatever we are having here. So whenever you encounter y of 0, this y of 0, it becomes 2. That is from the initial conditions. So here, we expect to have a 2s. So the 2s that we are seeing here, so that is the origin. And then y prime of 0 is 6. So we come here, so we expect this to be 6. So this 6 that you are seeing here is coming from these initial conditions. The same case, we have another initial condition here, y prime of 0, which is 2. So these 2 that we are having here. So having done reach there, then we have already applied. We have applied the initial conditions. We have already applied the initial conditions. So now the remaining task for us here to do is now to obtain Ly. That is the next remaining thing. You need to make Ly the subject. That is the Laplace transform of y. You make it the subject. So if you make it the subject, then you are going to get this. That Ly will be equal to this. All of this. So it is very easy for you to see where these ones are coming from. Just by making Ly the subject. Having made Ly the subject and opening the brackets, if you open these brackets, then it will be simplified. It will simplify to 2 over s minus 3 to the power 5 plus 2 over s minus 3. So now this is the Laplace transform of y. But like L here, we have introduced the L. The L has been introduced. So we need to do away with the L. To get our solution, we need to do the L, the Laplace transform. So you need to do the Laplace inverse. You need to get the Laplace inverse for you to only remain with the y, which is the answer that is the expected. So by taking the Laplace inverse times Laplace. The L inverse times L is simply 1. So whatever you're having here. So it is simply 1. And then meaning that now on the left side you remain with y is equal to. So you need to get the Laplace inverse of this one and this other one. And from whatever you have previously, then you need to know how to play with those values. Like now for this first one, that is 2 over s minus 3 to the power of 5. So if you look at that nature, if you look at the nature of that kind of equation, you will see that it is borrowing. It is borrowing from whatever we have seen previously. So you see that it is borrowing from this. It is borrowing from this concept. So you need to be able to write the given equation in this form for you to know it is exponential at and then times t to the power what? First of all, you need to write it in this form. So going back to whatever we have. So from whatever you have, we have 2 over s minus 3 to the power 5. So as you can see, so these two. So what do you expect? If you look at the power 5 that we have below there, s minus 3 to the power 5. So that 5 is the one that is going to help us. That 5 is the one that is going to help us to know the value of the n. We need to know the value of n. So we know that below there, we normally have n plus 1. We normally have n plus 1. So meaning 5 is equals to n plus 1. So what is this n? Then n is 4. That's why you are seeing that here we are having 4 plus 1. And then meaning none of the n is 4. So you need to have on top there 4 factorial. But if you look at 4 factorial, it is simply 4 times 3 times 2 times 1. Meaning, already it is more than whatever you're having there. So you need to divide by 4 factorial for you to be able to remain with the original equation. So if you look at that, it is basically a matter of balancing. You're trying to balance that equation. So, and then the other one, as you can see it is basically also borrowing from the other concepts for getting the inverses. So it is borrowing from this one. So it looks like that. 1 over s minus a is equals to exponential at. So looking at that keenly, in our case here, we have 2 over s minus 3. So as you can see, if you remember, the general case there, we had 1 over s minus a is equals to exponential at. Then for our case, we need to factor out 2 because 2 is not required in the numerator. Then so we'll have 2 exponential. So this will be exponential 80, or basically exponential 3t. That will be exponential 3t. So meaning that now our answer will basically reduce to that. Our answer will reduce to that. So it is very clear for you to see that. It's very easy to follow and see why we are getting such kind of a solution. So another example that we have here is this one, y double prime minus 10y prime plus 9y is equals to 5t. And then the initial conditions are given here. So the first thing for you to do is to get the Laplace transform of y prime and y double prime. First of all, you write your equation in that form. After writing it in that form, then you apply the Laplace transform on both sides. So it's very clear that you'll get that. So it's very clear that you are going to get this. That is from that transformation, because the Laplace transform of 5t, 5 is a constant. So if you look at the Laplace transform of t, Laplace transform of t from this table. So we know that t is n, the power of n will be 1. The power of n will be 1 as far as t is concerned. So if you replace that is the n by 1 in this second statement here, you replace n by 1, then you are going to get, you are finding the Laplace transform of t, which will be equal to 1 factorial over s to power n plus 1, which is 1 plus 1. So it is 1 factorial over s squared, which is 1 over s squared. So coming back here, then you are going to see that it is clear that this part will be 5 over s squared. So then applying the initial conditions. So you apply the initial conditions the way I have shown you. Then you are going to arrive at that point. So from there, you will be required to expand the bracket and make Ly the subject. That is the second step. You need to make Ly the subject, so which will give you this. that we have there. So having obtained the Laplace, the Ly, you just now transform. You get the Laplace inverse. You get the Laplace inverse on both sides for you to be able to find the solution to that differential equation. For you to be able to find the solution to that differential equation, then you require to get the Laplace inverse for you to be able to find that solution for the differential equation. So I've just said that these are some of the methods. The Laplace transform is another way of solving the differential equation. So from our previous lectures, you saw that there are other ways. There are other ways of solving these differential equations. So I think for today, we shall end at that point. So ensure you are able to go through this area and get everything clear. This area of Laplace transform is basically like 3 marks. So long as you know how to apply the Laplace transform, you know how to apply the initial conditions, you know how to make Ly the subject, and then you get the Laplace inverse, and then you are done. So it is as easy as that. It is as easy as that. So there are some questions there that have been provided, and they have some answers. So have a look at them, ensure that you are able to get the answers that are provided there. Otherwise, if nobody has a question, continue reading. So in our next lecture, we will look at the power series solutions, and I think this will be will form the last part of ODE. So continue reading the previous notes, that is the lectures 1 up to where we have reached. Continue revising so that life will be easy for you. Life will be easy for you. So guys, if there is no issue, enjoy your evening.